that's Laplace Transform Lecture 3, and I'm going to finish this chapter. So I started with the step function UCT, and no, I ended up here. What if I have this function multiplied by another function? And I showed you that it basically truncates. So if it starts at C, it just kills the function before that point C. So if I have a function like this, say, this is ft, say, the graph of ft, then you see ft will be something like this. So it kills the function. So it is 0 before this C, and it's the same thing after point C. Same. So it's good for like a force that starts at a certain point in time. Like suddenly there is some boom happening, and so you suddenly have a force like this, or a forcing function like this. It's not continuous, or I mean, before this point it's not continuous. It's like a shock or like a switch or something. But anyway, so this UC does this to ft. So this is in fact UC times ft. Now, we are mostly interested in this one, not this one. We are interested in this one because we end up with e to the power minus cs times fs, and we want to find the Laplace inverse of that. So this one is in fact what I will prove, and then because Laplace transform is one-to-one, it's linear function, it's a one-to-one linear function, so if the Laplace of this is this, then Laplace inverse of this is this, as you can see in this box. So let me so Laplace transform of this function is starting from 0 to infinity, e to the power minus st, e to the power, I'm sorry, okay, that's uct, uct f of t minus c dt. So this means that it should start at c, and there is nothing before that point c infinity, e to the power minus st, and then it goes away, and f t minus c dt. Now t starts at c, so t is starts at c, ends at infinity, so t equals c. So if I say t minus c, well, t minus c will be 0. So if I let sigma be t minus c, then d sigma is dt, and it starts at 0. So let me erase this. So and also we have from here, if we let this happen, then I have this, and also t is sigma plus c, right? Sigma plus c. So this integral will become from 0 to infinity, and nothing happens to infinity. Infinity minus plus anything is infinity, and this goes away. I have c as t, so t was sigma plus c, and this will be f of sigma d sigma. Okay, so this is s sigma minus, it is integral 0 infinity e to the power minus sc, right? E to the power minus s sigma f sigma d sigma. So let me write here, I have enough space. This one has nothing to do with sigma, so it comes out e to the power minus sc, then integral 0 infinity e to the power minus s sigma f sigma d sigma. But what is this? This thing is in fact Laplace transform of f. So G. No space. So this will be e to the power minus SC L of F. Now this sigma is dummy, so I can still write Ft, which is e minus SC Fs. And that's what we have here. This guy here. Okay, so it's simply a change of variable, and the change of variable changes the limits of integration, and that's it. That's a simple change. Okay, so we have this here. Let me erase this and write this somewhere up here, and so I can refer to that. So U C T F T minus C L and L inverse goes to e to the power minus CS Fs. Okay. And back to. Now, what does this tell me regarding this? So, if I have this, but how can I find this? So, let's say given this, find Ft, which is L inverse of Fs. Okay, just look at the table, use the table to find L inverse of Fs. Then L inverse of this, e to the power minus Cs Fs, will be U Ct f of t minus c. Okay. That's all. So you basically just put this e to the power minus cs to the side and find a Laplace inverse of Fs, use the table, then apply this theorem, this simple theorem, and you have the function Ft. Okay, so let me give you some examples. Let me erase this, keep that over here. I'm not sure about this one. Let me see, given a function this, oh yeah, Fs is 1 minus e minus 2s. So example, this one is good. Fs is given as 1 minus e to the power minus 2s over s squared. Find L inverse of this. Okay. So let's see. So I have L inverse of 1 minus e to the power minus 2s s squared. I know that L inverse is linear, so it is L inverse of 1 over s squared. Minus, in fact, L inverse of, as I said, put this, bring this out, times 1 over s squared. Okay? So basically I need this one because it's L inverse of 1 over s squared. Okay, let's look at the table, and 1 over s to some power. S. So we have to find this. Let's write this. It says that t to power n will be n factorial s n plus 1. N factorial s n plus 1. Okay. So if I have 1 over s2, then n is 1, right? So that is in fact 1 over t. So this is 1 over t. So back to this. L inverse of this thing is 1 over t. Then minus, that is ft minus c. What is c here? Let's write c carefully. So c is, this is you see that's e to the power minus ct. So c will be 2, right? It's not minus, so it's 2. So t minus, it is u 2t times ft minus c 1 over t minus 2. Okay? See, why did I write that? That's not minus, that's in fact t. That's another. Why did I go with it? This is t. Okay. So that's t, and this is t minus 2. Okay, so, yeah. So I can just say it is 1 minus u2 times t. And then plus u2t or something like that. Well, that's enough. That is. So that's how you find it, just by looking at the table and not making a mistake like me, and you can find it easily. So let's do a problem. Another problem, I mean, in solving a differential equation. How does this work with a differential equation? So let me choose one from the book because I need the solution. So this is in fact wow, no, that's not easy. But there's 2 examples, so it might take some time to do this, but let's do it. So 2y double prime plus y prime plus 2y is gt, and gt is u5 minus u20. Is u5 minus u20. Okay? So, what is it? u5 minus u20. So, let me first give you some examples of combination of these functions and how it works. So, u5 minus u20. This looks like this. So you start at 5, and it's 1 here. So you just go to 20, say. Then it's minus. Minus will just come down by how many units? 1 unit. So you just come down by 1 unit, and you continue, because then after that it is 1 minus 1, 0. So you have 0 here, and 0 here, and it's 1 here, right? So this is not included, and I'm not sure which one is not important. Well, that's not important because we're integrating. So anyway, it looks like this. So it's like a switch. It opens here, 1, 1, 1, 1, then suddenly dies. So if I multiply this by a function, ft, what happens? So if I multiply this by, say, this ft is like this. If I multiply this by ft, then it's like restricting ft from 5 to 20. Right? And then it's 0 here. So it's like some force is applied. It's like some force is applied between 5 and 20. So it's like 5 seconds to 20 seconds or something like that. Force is applied. So it's good to restrict if you want to just apply a force. It's like a machinery that is a force applies and stops. No force then applies. So you can even multiply this by, if you want this to be, say, 15, for example, then you stop, say, 5 seconds, so 25, then you need 15 again, so 15 will be 40. So you write as multiplied by that. So you get this force applied like everywhere for 15 seconds, every something like 5 seconds. 5 seconds, 15, 5, 15, 5, 15, and so on. By combining or by multiplying this by a function ft, you can come up with amazing combination of forces applied to certain, say, systems, like this system. Now, what if I had say, well, let me change this to minus, say, 5, not 5, let's say 3. Then plus, say, 8 u, that's 20, let's say 35. Right? So let's see. This one will be, you start at 5, it's 1 here, you go up to 20, then you drop 3, so you're at minus 2, so you're at minus 2 again, and minus 2, and how far do you go to 35? 35, you're at minus 2, then at 35 you go up by 8. So 8 minus 2, 8, that's 6, so you go up by 6. You are here. You continue to infinity. Because there's nothing to make this 0, so it's like that. And this is like 6. Okay? So that's it. So these combinations can give you amazing combinations of. Now, if I multiply this by a function ft, you can see what happens to that ft. The ft is truncated and so on. You multiply it and then it goes below, above, or something like that. So now you can play with these things a lot. And those of you, as I said, who study control engineering, electrical engineering, you will see, because they're like in electronics or electrical engineering, there are in fact lots and lots of force functions that look like that. So it's like a pulse, boom, boom, something like that. So it's like a switch or something. So let's see. Let's apply Laplace L y plus y prime plus 2y. And we assume that y at 0 and y prime at 0 are both 0. So let's just assume it starts at 0. And on this side I have L of u5t minus u20t. So this I have s squared plus 2s squared plus s plus 2s L of y, and on this side I have e to the power minus 5 s minus e to the power minus 20s. Okay, so over s, yeah, if we get the 1 over s, if I get there is 1 over s times this. Okay, so Ly will be this guy here on top divided by s times 2s squared plus s plus 2 plus 2. There's no s here. Plus 2. Okay. So I said just leave this out of the picture for the moment and let's find L inverse of this 1 over s times 2s squared plus s plus 2. Okay. Now let's see, is this irreducible? How do you find out? It's very simple. You in the quadratic equation, if the term under the radical, which is b squared minus 4ac, if this is negative, then it has complex solutions, and in a sense it is irreducible. So let's check that. B squared minus 4ac here is 1 minus 4 times this times this, so that's the 8 to 16. Okay, so this is irreducible. That is minus 15, so it is irreducible. That's the best way. Don't try anything, just do that. Now, so I have this situation. Well, I don't have enough space, so let me erase this, just write this over here. And continue, so I have some y. Okay, so 1 over s times 2s squared plus s plus 2, that's like a over s plus bs plus c over 2s squared plus s plus 2. So I have a times 2s squared plus s plus 2 plus bs plus c times s over partial fraction. So, well, let's see, if I set s to be 0, I will get rid of this and I can find a, so I have 1, but let me write it first. So if I set s to 0, that gives me, this is 0, so I have 1 equals 2a. So a is 1/2. Okay, so a is 1/2, and now I can find bs plus c. Well, I can just let s be 1, say. So s1 gives me 1 equals, this is 1/2. So this is 2 plus 1 plus 2, that's times 5, plus b plus c, and s is 1. So I have b plus c equals 1 minus 5 over 2, that's 1 minus 3 halves, right? So 1 minus that's 3 halves. And well, I can set S to be negative 1. Then I have 1 equals 1 half times 2 minus 1 plus 2 plus minus B plus C times negative 1. So 2 plus 2 is 4 minus the 3 halves, and so I have 3 halves here, and 1 minus 3 halves is minus 1 half. So on this side I have minus 1 half, and on this side I have B minus C. So B minus C is minus 1 half. If I add them, I get 2B equals minus 2. In fact, B is negative 1, and so 2C, if I subtract, is minus 1, so C is minus 1 half. So, okay. Let me check. So what was A? A was 1 half. Okay, so I will get, let me write down here. So I have 1 half here, and the B is minus 1 minus 1 half. Minus 1, so it's minus S, and minus 1 half. Okay. So let's erase everything. Do this. Oh, can't have it that much. Okay. So let me erase this because I have to. I need L inverse of each one of them. So L inverse of 1 over S. L inverse of 1 over S, what was that? That was 1, I guess. Yeah. Let me go back to the table and this one. So that is 1. Then I need L inverse of this thing. Okay, so I need L inverse. This is like the first time I'm giving you this kind of example, and you have 2S squared plus S plus 2. Well, I don't like this 2S squared. I need S squared. Why? Because I have to complete the square here. So I have to get S minus, say, A plus B squared, something like that. So I need to complete the square, and I don't need this 2 here. So I can factorize the 2. So this is the algebra. S squared plus 1 half S plus 1. On top I have minus S minus 1 half. Okay? Well, I don't know what I should put outside, but this one, there's a 2 here, so there is a 1 half coming out. So I can just write 1 half L inverse of this. There might be other factors coming out, but let's just get rid of this. Good. Now, how do I complete the square here? S squared, but let me, I think it's not easy to see when I can see this side. Okay, so I should complete the square here. So let me erase this and let's do it. So that's the second one. And so I have 1/2 L inverse minus S minus 1/2. And denominator will be S. Okay. So divide this middle one by 2. Right? And write it there. 1/4 squared. Then on scratch paper, you can write it on scratch paper, so just raise it to power 2, that's S squared, plus twice this times this, 1/2 S plus 1/16. A plus B squared is A squared plus 2AB plus B squared. Don't forget this is important. And A minus B squared is A squared minus 2AB plus B squared, right? So this is in fact this first one. Now look over there, I have +1 and I have +16. So what remains is in fact 15/16, right? 15/16. So this is this, and this is what remains because this is 1. So I have to write plus 15/16. That's how you complete the square when you're dealing this. What happened if I had 10 here? So if I had 10 here, then 1/16 plus something should be 10. So you would find this. So it's 10 minus this, right? It's 1 minus this. So this guy here is 1 minus 1/16. If I had 10 over there, that would be 1/10 over 1/16. This number here. So anyway, this is. You can, in fact, check this thing. Raise it to power 2. Add this. If you have that, then this is correct. Now, why am I doing this? Remember, the Laplace inverse of sine and cosine looks like this. So I'm basically trying to find Laplace inverse of sine and cosine, or e to power something sine, e to power something cosine, right? Okay, so let's look at the table and see if I can find anything like this. So let me. So in the table, I have things like this. I have L of e to power at, is it e to power 80 sine bt, e to power 80 sine bt, and that is a constant which is b over this thing, s minus a plus b squared, right? And for cosine, this is this. For cosine, I have L of e to power at cosine bt, and that is the denominator of this square. That is s minus a squared plus b squared, and here I have s minus b. Okay? So, somehow I have to come up, well, the denominator is here. From this denominator, I can figure out a and b. So I look at this, and I will find a and b for you. So what is a? That's s minus a, so a is minus 1/4. B squared is this, b squared is this, so b is square root of 15 over 4. Okay? So square root of 15 over 4. Let me go back, because I have to check the answer at some point. Yeah. So, what do I need? I need this and s minus that. And let me add them to b squared. So, This is minus a. Sorry, that's not b. It's minus a. So I need b on top, which is square root of 15 over 4, and I need s minus a, which is s plus 1/4 over there. Okay, let's see. Let's see if I can manipulate this to get those things. Okay, let me erase this. First of all, I can get rid of this minus sign because everything is like seems to be positive. So I write the minus outside. So I have s. I need s minus a, so that's s plus 1/4. Well, when I get rid of the minus, I have s plus 1/2, right? So let's see what I can get. I need this, and I also need b. So I also need plus square root of 15 over 4, right? I have s plus 1/2. Let's see what I have here. So the s is there, okay. 1/2, I have 1/4, so 1/2 comes out of this. I have 1/4 plus 1/4. And I need square root of 15 over 4, so I just write square root of 15 over 4 minus square root of 15 over 4, right? So this, let me write the denominator. So s plus 1/4 plus 15 over 16, and so I have plus what? So I have a 1/2 here. I have a 1/4, and this is 1/4 minus this. Right? Let me see. No. Let's see. This is not correct. No, I just need that. So what? That wouldn't work. What? And plus 1/4, right? So yeah, I need b. I need a multiple of b, which is this square root of 15 over 4. So I should turn this into square root of 15 over 4. Well, let me first separate this thing, then I will do that. So I have minus 1/2 L inverse of S plus 1 over 4, and the square over the square, S plus 1/4 square plus 15 over 16. Well, I know this is like cosine of something, and minus 1/2, then I need 15 over 14, so I just multiply by square root of 15, divide by square root of 15. So I have minus 1 over 2 square root of 15, L inverse of square root of 15 over 4, divided by the same thing, right? Divided by the same thing. Let me not write it, I don't have enough space. So, okay, so that gives me minus 1/2. L inverse of this is e to power minus 1/4 t. This one is cosine of square root of 15 over 4 t. This one is minus 1 over 2 square root of 15 e to power minus 1/4 t sine square root of 15 over 4 t. Okay. Whew. Let me. Well, I'm not going to double check. You double check it yourself. it's too much. But anyway, so let me, I have one and I have this thing, so L inverse of this guy here, L inverse of this guy, is this. So L inverse of this guy, L inverse of this will be, this one was 1/2 times 1, and this was minus 1/2. Well, I can put the minus 1/2 outside, so I have well, e to the power minus 1/4 t, e to the power minus 1/4 t. Then this one is a cosine square root of 15 t 4 t, and this one will be plus 1 over square root of 15 sine. Well, let me check. I think it's good. So that is L inverse of this Fs. That's L inverse of this Fs. Oh, okay. So L inverse of this Fs is this, but I need L inverse of e to the power minus 5s, this Fs, so let's call this Fs. Remember that was every t goes to t minus c. So this is minus 5, so I have c is 5, so that is everything goes to t plus 5. So this will be, this doesn't change because there's no t here. I have 1/2 minus 1/2 e to the power minus 1/4 times t minus 5 cosine over square root of 15 over 4 times t minus 5 plus 1 over square root of 15 sine of square root of 15 over 4 times t minus 5. So that is multiplied all of this by what? By this multiplied this by u 5t, right? And then L inverse of e to the power minus 20 t s 20s Fs will be u 20 t times the same thing, 1/2 minus 1/2 e to the power minus 1/4 t minus 20 cosine of 15 over 4 t minus 20 plus 1 over square root of 15 sine square root of 15 over 4 t minus 20. Okay, so then it is this minus this. So it will be this one minus this one. Okay, so the solution is just a giant formula. So the solution is this guy here minus this guy. Okay, so this is this top one minus the bottom one. Okay, so the solution is that. Now I know that is like a wow, that's such a big nasty function. But anyway, it's funny. So, and this was an example in the book. So I guess let me say, I guess it has. Yeah, there is a nice graph of that. You can take a look at the graph. It starts at, in fact, 5. It's 0 before 5, and you can see that it's just some interesting response. So it was like those two impulse, or that function I showed you, the simple impulse was applied to this system, and the system could have been like a spring mass, for example, with like mass 2 and spring constant 1. No, spring constant was 2 and the damping constant 1. So, and the response is this. Yeah, I know it's like such a big mess as a response. So that is, in fact, now if I had you can take a look at other examples in the book, and if like a function which is 0 up to some point, then it suddenly jumps up and down, then you can write it down as a nice function times some step functions, and then solve it with step functions. We know the Laplace transform of step function, and those two theorems, which is still here. This is a very useful formula, in fact, and you will be using it in practically and also in your exam. There was also another section here, and that is the impulse function. Well, that is also an interesting function, which I don't have time to discuss it. If you ever see that anywhere, you can read it from this book, or you can Google it and find what happens to impulse function when you apply Laplace transform. In fact, that impulse function, in a sense, is like an operator. So the integral of that impulse function is like something operating on a function. So it's another world, in fact. So I'm not going through that. Yeah. Well, some students, maybe in physics, they need that more than maybe engineering students. But anyway, maybe students in electrical engineering, they use impulse function a lot. So that's like a boom, and like this, boom, boom. So a sudden bump or something, and then it dies. So it goes up, comes down immediately. So that is an impulse function, and the definition and how to treat the impulse function is, in fact, in the book. That's the last section of the book, I guess. And well, it also has the convolution integral, which there's no time really to discuss the convolution. And so that was the chapter on Laplace transform, and I will start next chapter on systems of linear differential equations, and we have 2 more chapters, and then we finish the course. Okay, so have fun.